So, the previous session we have discussed about in the last phase basically that how to represent this average diameter of a heterogeneous group of heterogeneously sized particle sample. So, this is specifically important in relation to size reduction, right, which we often call it as comminution. So, the size reduction is a more broad term basically. So, why this size reduction is regarded as an essential unit operation in many process industry, that we have to understand first. See, in metallurgy the size reduction is essential because this run of mine and ore materials you have to crush. Just think of this process in the blast furnace where we have to powder everything, that from starting from the coal to the iron ore to other ingredients whatever you are adding. So, you have to reduce it to the powdery form. In coal industries also, before you feed this coal to the furnace, it is to be pulverized. That means it must be ultra fine, right, and that is to be fed in the furnace such that it can be fluidized, it can be pneumatically transported and fed easily through the burner, specially designed coal burners of this furnace. So, there are multiple domains where we have to go for this size reduction. Different inorganic process industries like cement and inorganic chemicals which are generally sold in the form of powder, there we have to use this size reduction. So, size reduction is basically a typical unit operation, a typical we can say also a mechanical operation where the size of these samples are reduced. What is the objective? The objective is to increase the surface area, right. So, the primary objective, size reduction. So, the primary objective to increase the surface area of the solid. Right. And how it can be accomplished? How we can reduce the size? We can apply 4 different types of forces upon applying the following forces. Number 1, compression, used for large scale feeds, run of mine materials. Second, impact, used to produce fine powders, right. These fine powders means greater than this 100 micron maybe. Third, ultra fine grinder or ultra fine, this is attrition, used to produce ultra fine powders, 1 to 50 micron size maybe. And shear, used in cutting machines. Right. So, compression, impact, attrition and shear. So, based on the size, actually you have to understand that this is the scale of size. It's as the size of the feed progressively decreases, definitely up to this. Here is out of the typical size reduction. Here the mechanism is totally different, right? Here it's a cutting machines, so that also reduces the size, but generally we do not consider these cutting machines in this typical size reduction group. So the compression, impact, attrition, and in this way the size reduces. So initially the compression, we will see that majorly it is used in crushers, right, where the feed is run of mine materials, any size it may be, it reduces to the size of 1/4 inch rather. So next it is the impact, which is used in fine grinders, and next it is attrition for ultra fine grinder. You see the typical household nut cracker is an example where we use this compression, right. Hammer we use the impact, file we use the attrition, and the set of scissors we use the shear. Okay. So that's the idea, that the major fundamental forces and the baseline idea behind these size reduction devices. Now size reduction devices, see, the comminution is a generic term for size reduction and broad classification. Of size reduction devices. Number 1, crusher. We will discuss this classification in detail, but here it is a broad classification. So crusher, where we use compression, grinder, we use impact, ultra fine grinders, we use attrition, and finally the cutting machines, as we have mentioned, as I mentioned, that we use here the shear. Right. Now, how will you study this performance of those machines? Just like reactor, compressor, pump, we have studied, distillation column, etc. we have studied, right? So there the idea for any process device, how to study, here it's a very basic one, how to study a process device. Introduce an ideal machine. Example, reversible compressor. Right, or equilibrium column, or MFR. These are all idealization, right? So we go for an idealization initially, and next we compare the actual device with the equivalent ideal device upon introducing some empirical parameters. Like for reversible compressor, what we introduce? This efficiency. For equilibrium column, right, there also we introduce this Murphy overall or point efficiency. For MFR, what we go for? We introduce tank in series model. In RTD studies, what we have discussed. So these are non-idealization, or rather we should write not in tank in series, it's a model. What we use these RTD parameters. right. So thereby we actually can have a comparison between the ideal machine and the actual machine. However, the problem in the size reduction device, a huge gap between the ideal and the actual. Right. Definitely here we can have some gaps, but it should not be 100% gap. Right. But in size reduction, nearly the gap is 100%. Specifically from the perspective of energy usage. Right. So energy usage, you see that if we think of an ideal crusher or grinder or any other size reduction device, what we will think? That energy what we have to give, the surface energy we are additionally, specifically in terms of surface energy, we know how much surface area we have increased, that we will simply multiply by the specific surface energy, right. So specific surface energy, that is surface energy per unit this mass multiplied by the mass flow rate. So that must be the requirement of energy for an ideal crusher or grinder. However, in real life, this energy whatever is required in this crusher is nearly 100 times higher, right. So there is a huge gap between the real crusher and the ideal crusher. So the typical idealization and this type of approach will not work here. It's not going to work here. Additionally, we can think that ideal crusher will produce, specifically I have mentioned that this is in terms of this non-idealization or this non-ideality or specific the deviation of this real crusher from this ideal one, that is huge because of energy usage, the inefficiency of the real crusher to use the energy in this actual deliverable form. But the point also, this non-ideality also creeps in because of size. Like in ideal crusher, the product we expect that must have a uniform size, right. So this uniform sized product is never achievable in reality for real crushers or grinders. And to some extent shape, though if I deliver or if I feed that specific machine with a uniform feed size, most of the cases it will deliver uniform product size, right. So shape is not a big question, size is definitely a question, but not exalted to that extent. However, energy is the specific issue where the non-ideality is huge, right. So we have to think about the specific methodology what we follow in modeling or in formalizing any process device, right. So you see this is here in the handout we have some basic introductory sections where we have discussed about these issues of energy and the size as well as shape, and the ratio of diameter to the largest to the smallest particle in any size reduction device is around 10 to the power 4. So, and because of this extreme variation in size of the intermediate particle relationship, adequate for uniform size must be modified when applied to such machines. The term average size, that's why is so important. So let's have a discussion regarding the energy usage. See, mostly the standard equation what we derive from basic physics of that system is not going to work, as we have to include the empirical parameters of efficiency, which has got a very, very small value like 0.6 to 1%, right. That means 0.006 to 0.01. So that's the range of efficiency for a crusher. So you can understand that whatever we are going to calculate theoretically, if that specific factor changes a little bit, there will be huge error, right, in our calculation. So though we will be discussing this, but it's majorly restricted to theoretical domain. See, the power, or definitely it is the electrical power, just very similar to pump. What you deliver, first it is the mechanical output of the device, right, and here we call it mechanical efficiency, just very similar to centrifugal pump, whatever we have discussed. So this mechanical power output of a device, or mechanical power output of a device, we can actually measure if we run the device dry and simply experimentally evaluate the brake horsepower of its shaft. So mechanical power output of a device is calculable, and this mechanical efficiency is not a big issue. It may be more than 90%. However, there is a huge drop, right, and finally it will deliver the surface energy. And here comes the term, the empirical term. What is the specific issue, right? It's called the crushing efficiency. And this crushing efficiency is mostly less than 0.6 to 1%. So here this is the source, this cascade specifically is the source of non-ideality. Now we have to understand that why we have this huge drop. See, whenever you have feed, you are actually compressing it or giving attrition or giving this impact, whatever, right. So in this process, you are storing energy in the material, right, just like in a coiled spring. As you are storing energy, whenever you compress this spring, you are basically, or elongate the spring, you are storing elastic energy. Similarly here in size reduction, whenever we are applying this force of compression or impact or this attrition, actually we are storing the energy into it. We are delivering energy to it, right. And next, it breaks down into pieces. Because it exceeds the ultimate strength. The stored energy basically exceeds the energy of the corresponding ultimate point. So it breaks into fragments. And whenever it breaks, mostly the energy, the stored in the previous stage, the stored energy is lost in the form of heat and leaving only available surface energy, right. And because of that, we have a very low value of crushing efficiency. When we do this actual calculation, we will neglect this part, that no heat is being lost, whatever energy we are giving, definitely that is being used to create the new surfaces. That means this is equivalent to the surface energy. So that is basically the fallacy of our idealization, okay. So with this understanding, as I have mentioned, that theoretically we have to calculate something. So if I have a size reduction device and we are here delivering a feed with specific surface area, let us say we are changing the nomenclature AWA, A suffix WA, and here this is the product, the specific surface area is AWB. The product is marked as stream B, feed is marked as stream A. So, surface created per unit mass is definitely AWB minus AWA. So, energy or difference of surface energy per unit mass is equal to ES into AWB minus AWA, where ES is the specific surface energy, right, equivalent to the solid air surface tension, right. It is basically sigma SA, okay, and its unit will be in joule per meter square. So, the power required, the ideal calculation, is m dot into ES into AWB minus AWA. That is basically the power, ideal power, which we can calculate from here. Now, you see that this is the available energy here. If we have to calculate the mechanical power output, we have to divide it by eta C, which is the crushing efficiency, and here the non-ideality, huge non-ideality creeps in, okay, and again by eta M. So, P, which is the actual power required, is equal to m dot into ES AWB minus AWA divided by eta C into eta M. So, we can write this as P by m dot is equal to ES eta C eta M AWB minus AWA. Now, that is the specific surface area. Now, specific surface area is related to the size and sphericity. So, you see that just we have calculated the specific surface area AW as 6 divided by dP into rho p into phi, right. So, here we can write that P by m dot is equal to 6 ES eta M eta C rho p within bracket this 1 divided by d bar. Here we use surface volume mean diameter for the product minus 1 divided by d bar SVA. We can also think of different sphericities associated to feed and product. So, this becomes my actual equation what we can derive from theory. But this will never be a realistic equation because of the term eta C, which you have to conduct experiment. For eta M, again we have to conduct experiment, and that eta C varies widely, right. Eta C is 99% lower. This eta C, see whatever term you calculate, if you divide it by 0.01, it will be 99 times higher than whatever we have estimated theoretically. So, theoretical calculation actually has got no meaning here, though we have to learn it because this is the background. So, if you see that we assume the feed and the product are of same shape, that is phi b equal to phi a, let us call it phi. So, P by m dot is equal to 6 ES eta C eta M rho p into phi 1 divided by d bar SVB minus 1 divided by d bar SVA. So in 1867 probably, right, Rittinger, he proposed this 1867, the empirical equation for size reduction. And what he did, he grouped whatever we are actually deriving from theory, he grouped it into a single constant. And it is pretty logical because this term has got no meaning because of the term eta c. So P by m dot, which becomes the Rittinger's law, Kr into 1 divided by d bar SVB minus 1 divided by d bar SVA. So that becomes the Rittinger's law. This is purely empirical because this Kr is to be experimentally measured. The constant, empirical. Why we are calling it empirical? As this is to be measured experimentally, and it varies widely over different types of machines for different types of feed, right? And whenever if you change the feed and product size, then also there are reported variations of this Rittinger's constant. So in 1885, let me check the year. In 1885, Kick proposed another law based on this is more, to some extent, bit more logical, right, based on the plastic deformation of the material, and that is called the Kick's law. Based on plastic deformation of the materials. That is Kick's law, which states that P by m dot is equal to Kk ln this d bar SVA by d bar SVB. Right. So both the Rittinger's and Kick's law, they are mostly of theoretical importance. You have to note that both Rittinger and Kick's law are of theoretical importance. They are not used practically. For practical use, we use the Bond law in 1950. Much later, it was proposed by. So this bond crushing law, somewhat more realistic method for estimating the power required for crushing and grinding, and proposed by Bond in 1950. Bond postulated that work required. So what is the postulation? I have an infinite feed size, very large feed. So this is very large feed, right? We reduce it to a size, product size d bar SV. So according to Bond calculation, P by m dot is equal to Kb into 1 divided by under root of d bar SV. That's the original Bond's law. Now you see that how we can apply it for size reduction devices. So product size d bar SV, if we write B, and product size d bar SV A, then the gap is basically the power estimate for the actual device. So from infinite size, one is going to give you d bar SV B, another is of product size d bar SV A, and this gap is the estimate of power required for the size reduction device. So Bond's law, usable form of Bond's law, P by m dot is equal to Kb 1 divided by under root of d bar SVB minus 1 divided by under root of d bar SVA. Right, that is the usable form. But still there are some modifications. This constant, we do not write the constant as it is, we do some modifications. What is that? There is some further secondary definition. We define something called work index Wi as the power, there is unit specific definition, as the power required in kilowatt hour kilowatt hour per ton of feed, such that infinite or an infinite sized feed is reduced to a product of a size where 80% of it passes through 100 micron screen opening. Right. So this is the specific definition of work index. It's power specific. Right. It's unit specific. So P by m dot, P is in kilowatt, m dot is in ton per hour. So this is equal to work index, right, for a product size which passes through this 100 micron screen. So if I write 100 micron, 80% of the product passes through this 100 micron screen. So d bar SV is 100 micron is equal to 100 into 10 to the power minus 3 millimeter, right. So it is 0.1 millimeter. So 0.1 millimeter. So it is 0.1 and it is also unit specific, it is millimeter. So Kb becomes this W.3162 under root of 0.1, 0.3162 Wi, right. So we can modify the Bond's law. This Wi, we have the table for different materials. So this has been standardized. So Bond's law in terms of Wi. What you can write? P, now it must be unit specific. P is in kilowatt. M dot is in ton per hour. This is 0.3162 Wi. Then 1 divided by d bar SVB minus 1 divided by d bar SVA, and these two must be in millimeter, right. So if you are using the work index definition and work index value from a table, so you have to use this formulation, and such is the unit specificity of this equation, right. Now that's the basic idea of this power estimations for size reduction. Next, let's discuss about some idea about this size range on which the different devices operate, right. Say just the crusher, right. The crusher, here we can have run of mine materials. It reduces to a product size 1.5 to 2.5 centimeter. This is a primary crusher. Now, if you feed it to the secondary crusher, or you can feed the primary crusher outcomes to a secondary crusher, it reduces to a product size of 1/4 inch, right. 2.54 is 1 inch, so 1/4 inch size, right. So, grinder reduces the crushed feed to powder. So, this is the feed to a grinder. It produces a size, the product from an intermediate grinder. So, this is the intermediate grinder. It reduces to size around this 40 mesh screen. Most of the product 40, this is 40 mesh screen, and from the grinder it goes to ultra fine grinder. Right, and its feed size must not be less than, or it should be less than 6 millimeter, right, around 1/4 inch. The product typically varies in the size range of 1 to 50 micron. So, product from which corresponds to 200 mesh screen. And this 200, this 40 micron screen size, no, this one is not this 200 mesh. 200 mesh fine grinders product pass to a 40 this intermediate. Then if you feed it to the fine grinder, it will be producing 200 mesh, which is around 74 micron, right. So, what you can see here, that run of mine material you mostly feed to the primary crusher. It reduces the size to 1 inch around, right. Primary crusher product you feed to the secondary crusher, it reduces to the size of 1/4 inch. Now, this secondary crusher directly you can feed to ultrafine grinder as well, but there will be a severe energy requirement. So, that is why what we do, we feed it to the fine grinders, right, or intermediate grinder, which reduces to a screen size of 40 mesh. You can go for fine grinder as well, or from the intermediate you can go for fine grinder. It will reduce the size to 200 mesh, and 200 mesh if you feed to the ultrafine grinder, it will reduce to a size of 1 to 50 micron, right. So, that is the huge reduction of size whatever is achievable through the sequence of grinders in this series of grinders and crushers with appropriate sequence. So, let us have a classification of these size reduction devices. The broader it is not a broad classification, it is a particular this detailed classification we can say. So, first one is this detailed classification of size reduction devices. A is crusher. What are the different types of crusher? One, jaw crusher, where we have a fixed jaw, right, and a reciprocating movable jaw. And this opening size actually determines the size of the product. Here you can give any feed, and these jaws are mostly corrugated for a grip. Second, gyratory crusher. Here we have the double conical section where we have a disc which eccentrically gyrates in this opening. So this is the typical gyratory crusher. And third one is the crushing rolls, which we will discuss in details. B, grinders. And this is basically intermediate and fine grinders. So one is the hammer mill. Then impactors. Number two is these attrition mills. Hammer mill, rolling compression mills. Rolling compression mills. Here we have these roller mill, ball mill. These are the names. I am not going into the details. 3, attrition mill. 4, tumbling mills. This is very common, and that we will also discuss, which includes ball mill, rod mill, then ball mill, rod mill or pebble mill also, tube mill, etc. So hammer mill with impactors, rolling compression mill, attrition mill and tumbling mill. C, we have ultrafine grinder. Hammer mill with internal classification. There are meshes which will basically recirculate the take away the undersize and recirculate the oversize. This is called the closed circuit grinding, and the device is designed in such a way so that it's internally closed cycled. So hammer mill with impactors, with internal classifications. Agitated mill, fluid energy mill. And D, that is the cutting machines, dicers, slitters, etc. So that's the detailed classification of size reduction devices. As I mentioned, the crusher mostly use compression, grinder use this impact or to some extent attrition here, right. Here tumbling mill also use the impact. Do not have a misconception that tumbling mill uses attrition, mostly uses the impact. So fluid energy mills, agitated mills and hammer mills with internal classifications, which collectively belongs to this group of ultrafine grinder, they use the attrition, and the shear is used in cutting machines. So we will primarily discuss this smooth roll crusher, because the roll crusher, see what is a roll crusher? And this is smooth, or okay, let us not go by this detail. So here we have two rollers like this, which are kept face to face and rotates towards each other. Right. they rotate towards each other in this direction, and you can see that you give the feed here and the feed will be compressed and crushed, and as it is crushed it moves through the gap. So, the size of the gap, okay, let me move it a bit right. This is the axis, central axis. And let us assign the gap 2D here, right. This is the radius of the mill, and here we can have the particle being trapped, right. This is the feed particle. Now, definitely you can understand that particle, because of the friction of these two rollers, will be trapped and will be crushed, right. The typical dimension of these roll crushers, as you can see, that the diameter may be 2 feet, whereas the size or this length of the cylinders may be around 1 feet, right. That is the typical size for small scale operation. You can also go for this 6 feet diameter, right, whereas its this length will be 3 feet around. Now, roll crushers, sometimes why I was saying that this is a smooth roll crusher, there are teeth on the surface. So, this is called the spiked roll crusher, and which are mostly used for soft feed like charcoal, bone, wood, etc. But for hard feeds you should not use this teeth because they will be damaged. And these spikes mostly they are used for smooth gripping. So, and the rotational speed you see it may vary, right. The rotational speed it may vary, and it is around 50 to 300 RPM. The N is 50 to 300 RPM. Now, what is important, because there is a mathematical formalism associated. See, when this particle is gripped, then we can draw a tangent and actually it will meet at this point. And this angle is called the angle of nip. Here we can say the particle is nipped and it will be crushed, right. Let us say the radius of that particle is r. Let the angle of nip is 2 alpha, that means this angle and this both are alpha, the radius is r, right. So, angle of nip, capital R and D, they are related. Why? Because if you just join these two centers, so this is r plus r. Now, if this is alpha, see this is alpha, this is 90, this is 90 minus alpha, so this is alpha as well, right. So, this is r plus r, this much of this triangle is r plus d. So, alpha is cos inverse of r plus d divided by r plus r. So, once you know the opening size, the size of this particle, right, and the size of the roll, you can actually calculate this alpha. But generally what happens, this alpha is close to mostly uniform and the value is around 16 degree. Or alpha is basically 16 degree, which means the angle of nip is around 32 degree. So, for most of the cases, alpha is around 16 degree. So, you can calculate, and that is why because we have a fixed ratio of this diameter and length, and for that there is a fixed particle size which will be nipped. So, what we want to calculate here is that this material, whether it will be crushed or not, it depends on this angle of nip and the coefficient of friction, right. You see that there is a normal reaction force. At this point, there is a normal reaction force, and we can write it here. Let's call this normal reaction force as Fn. And there is a tangential force in this direction as well, which is the force of friction. Let's say it is Ft, right. So, this Fn, we can have two components. So, this component, the vertical component, is Fn sin alpha, whereas this one, there is also a vertical component, and this angle, you see, this is 90 degree actually, this total angle is 90 degree. So, this must be also alpha, right, because you can calculate here for this right angle triangle, this is alpha, this is 90 minus alpha, this angle is 90. So, obviously, this much is alpha. So, if the material, the condition for crushing, let me describe the condition for crushing. We can write that Ft into this cos alpha must be greater than Fn into sin alpha, because this is Ft into cos alpha is a vertical downward force which will move the particle towards the gap between the two rolls, whereas the Fn sin alpha will push the particle in the upward direction, right, which is against the crushing, and this is favoring crushing. So, if the favoring force is greater than the opposing force, then definitely crushing can be accomplished. And again, you see Ft, the tangential force, is coefficient of friction into the normal force. This is the typical formula of friction we have. So, evidently we get that mu must be greater than tan alpha for crushing, right. So, once we know the particle size, the diameter of that particle and the gap, which is the product size basically, we can calculate alpha, and knowing the surface of these two rolls and more precisely the coefficient of friction between the roll and this particle, we can get the value of mu. So, if mu is greater than tan alpha, crushing can be accomplished. So, that is the idea of the roll crusher. We have a mathematical kind of formalism associated with roll crusher. So, that is why we have to study this. So, again here we have used the word tumbling mill, and there is something called ball mill. So, we will discuss about this, because again there is some mathematical equation involved here and what is referred as critical speed. So, you see a tumbling mill, a continuous tumbling mill, how it operates. So, it is a double conical kind of equipment, slightly tilted in the horizontal direction such that there is a smooth flow of slightly tilted, it is less than around 2 degree, right. Here we have the gear, and this will be intermeshed with the gear of the motor. Right. And this double conical chamber, which is internally steel lined, is filled with balls, rods or cables. Here we are discussing about balls, such that the balls, when the mill is at rest, occupy nearly half of this volume. The balls may be replaced by the rod, but in that case there will be no conical section, it will be cylindrical. Now as the mill rotates, what happens? Let's see the cross section. The balls will be moving up, right, because of the centrifugal force. But from this height, it will move down with a high velocity and create an impact on the feed material. So this impact, because of that impact, the material breaks down into pieces. So size reduction is accomplished. So as we rotate that mill with a higher speed, it will be moving towards some higher height, but definitely after some threshold of critical speed, the ball will be moving. Without detachment from the roof, the ball will be moving to the other side, and there will be no crushing or no grinding at all, and that is to be avoided. So this is the speed limit for these ball mills. Okay? So that's why the idea of critical speed is so important. So you see that, let me describe some of the salient features. The load of ball in the ball or tube mill is normally such that when the mill is stopped, the ball occupy about half of the volume of the mill. I have discussed it. The void fraction of that in the ball mass when it is at rest, it's typically the property of the sphere, it's around 0.4. The grinding may be done with dry solids, but more often it is being done with suspension, because there is a smooth flow of the slurry, right. So it is in suspension, the solids are in suspended forms, it comes here and the ball, this mill rotates, so ball moves up, they get detached from the roof and create an impact on this machine. So create an impact on this material over which it is falling, right. When the mill is rotated, the balls just whatever I have stated, the faster the mill rotates, the faster the balls are carried up inside the mill, and the greater power is consumed. The added power is profitably used because higher the balls are when they are released, right, the greater be the impact at the bottom and larger the productive capacity of the mill. If the speed is too high, whatever I have mentioned as critical speed, that is also stated, the speed at which the outermost ball loses contact with the wall of the mill depends on the balance between the gravitational force and the centrifugal force. And what type of balls we use? We can use these metal, then zirconium balls. For intermediate and fine reduction of abrasive materials, tumbling mills are used. So let's now, what is more important instead of this description is that we have to calculate the critical speed. Because if we know my speed limit, I can operate it with 50 to 80% of that speed. So let's think of this cross section, and here we have the ball which has got a radius r, right. This radius of the mill is r, right. So gravity will be this Fg, and here we have the centrifugal force Fc, and this angle is alpha. Now you see, what will be the gravitational force Fg? It is m into g simply, where m is the mass of the ball. And what is the centrifugal force? What will be the centrifugal force? We know that it is m omega square r, right. So m omega square r, r is r minus r. So this centrifugal force has a component, so we have m omega square r minus r into cos alpha. Even at that position, it is not getting detached, or just about at a point to be detached, that m omega square r minus r into cos alpha, right, must be is equal to mg. Or rather, we can write this cos alpha on this side because we have to balance it in this direction. So, if the ball passes through the highest point, the cos alpha is 1 because alpha is 0. So, at this point, if it is perfectly balanced, these two forces are balanced, then as it moves to this side, the centrifugal force will further increase because there will be the component of the centrifugal force will be further increased, and the gravity or the centrifugal force here will be remaining the same, but the gravity will increase because cos alpha is decreasing as alpha is increasing from 0. So, we set alpha equal to 0 degree, right, and m into 2 pi n is RPM into r minus r is equal to m into g. So, m cancels out and we can easily find that critical speed NC is equal to 1 divided by 2 pi under root of g divided by r minus r. So, that is the formulation for critical speed, right. So, we must operate the mill at 65 to 80%. So, N operating is 65% to 80% of critical speed NC. So, that is the idea of critical speed and very basic discussion regarding the tumbling mill. Now, let us discuss about the last topic, which is the open circuit and closed circuit grinding. This is pretty simple, as you can see, that open circuit and closed circuit grinding. See, I am using here a gyratory crusher maybe. This is a typical representation of a gyratory crusher. This. Here you are giving the feed and here you are withdrawing the product. Now, what happens? Intermediate here inside the device, the already ground material which has attained the desired size is again actually circulating back again and again, right, because you are allowing for some residence time, and over that residence time, say a large material has already reduced in size and it has reached the desired limit, but still it will be circulated as you are not withdrawing the product, right. So, this is a severe wastage of energy. And that you can minimize if you continuously withdraw the product, screen that, resolve it into 3 or 4 fractions and circulate back the oversize again back to that this crusher. So, here we attach a screen, and that we are going to the idea of closed circuit grinding. So, this is the oversize, we circulate back to the crusher, right. This is the intermediate, we may feed that in a rod mill. And this is the fine which will feed or mix up with this rod mill product. This is an example, not the universal diagram, and you feed it to the ball mill, right, and ball mill, the product of the ball mill will be subjected to or will be fed to a centrifugal clarifier. And we will get the product slurry here, and the oversize will be repulped because the ball mill is doing wet grinding here. See, water, repulper, and we will feed it back to the ball mill. So you can see the idea. This is a overall diagram. The intermediate, the oversize is circulated back, the intermediate, or you can taking the undersize. If you have two screens only, you can taking the undersize. That is basically the diagram of closed circuit grinding. But here we are actually extended the diagram up to the product slurry formation. So we are using for the intermediate a rod mill, and for the fine we are using a ball mill. This ball mill is grinding wet, the rod mill is grinding dry, because the ball mill is feeding the wet slurry, reduced wet slurry, to the centrifugal clarifier, which splits it into product slurry and the oversize, which is repulped again upon adding water and fed it to the ball mill once again. Right. So that's the idea of closed circuit grinding. Okay. So that's all about the size reduction device. What we have to note here, the classification, the type of forces what we use, the different power calculations laws or power laws, that is the Rittinger, Kicks, and more importantly the bond law. In bond law we have to note this definition of work index and the unit specific form of this Bond's law, which is of real utility. And then we have the classification, the detailed classification of the size reduction devices into crusher, then different types of fine and intermediate grinder, ultra fine grinder, and cutting device. And out of all these devices, we have specifically studied the roll crusher because there is some mathematical perspective associated to the angle of nip and the coefficient of friction between the roll and this material to be crushed, and the condition is mu greater than tan alpha, where alpha is half of the angle of nip. And finally, the idea of critical speed leading and critical speed in case of tumbling mill, where this is the speed limit of the tumbling mill and we should operate the mill with a speed which is 65 to 80% of the critical speed, and critical speed expression is 1 by 2 pi under root of g divided by capital R minus small r, where capital R is the radius of this mill, where small r is the feed size, right. And finally, we have discussed about the open circuit and closed circuit grinding. So in the next class, we will discuss about the sedimentation and thickener design.